All right, hello everybody. So welcome back to Math Background for Machine Learning. I still can't get my Surface Pro to work, so we're streaming again from my laptop, but this time I actually had a little while to check the settings on my laptop, so hopefully streaming is going to go okay. Please let me know if not, and we'll try to fix it. So last time around, we were, in the first part of the lecture, we had a little bit of trouble with talking about the set of notes on feature transforms and such. So I'm just going to go briefly over that at the beginning of lecture today, and then we'll move on to new stuff. Looking at the poll, it looked like it was sections 4 through 7 of the notes that didn't come through. So let's go through those. So we're talking about multivariate regression here, and for multivariate regression, it's common to use a feature transform. In other words, instead of modeling y equals w times x, we model y equals w times phi of x. And this feature function, phi, it can change x however we want in order to make regression work better. So, for example, here's a very simple feature function, phi of x, which has it starts from 2 components of x and it makes 3 components, just copies over the first 2 and it adds the product. And the key thing about a feature transform is that we just do it at the beginning before we even start doing the pre-processing steps for our regression, like centering or scaling the variance of our features. And so it's like you just set it and forget it, right? Once you figure out the feature transform you want, you transform each one of your input vectors and behave as if the transformed vector was your original input. And you can do a lot of interesting things this way. One of them is illustrated actually even in this simple transform, which is to add what's called an interaction term. So there are two original coordinates of x. Let's say they're binary, representing whether we've treated a patient with one medication and whether we've treated him with a second medication. And then the output y, let's say that that's the severity of the patient's symptoms. So in this case, when we do the regression, the coefficient of x1 is the effect of medication x1 on the patient's symptoms. The coefficient of x2 is the effect of medication 2 on the patient's symptoms. And then the coefficient of this interaction term, x1 times x2, well, without it, what we would get is that we would predict that the effect of taking both medications would be the sum of each of the individual effects. And so what the third coefficient in the regression lets us do is it lets us move away from that default model. In other words, if there's a medication interaction where the effect of taking both medications is different from the sum of their individual effects, then that's captured in the last coefficient. All right. So as well, another useful feature transform is variable selection. So if we know ahead of time some components of x are going to be helpful and some aren't, then we can just drop the unhelpful ones. And if we don't know ahead of time which ones are going to be helpful, there are a whole bunch of algorithms for trying to figure out which ones are helpful and design that feature transform that drops all of the unhelpful ones. And hopefully today we're going to get a chance to look at one of them, which is called forward stage-wise regression. Okay, so even after this nonlinear or possibly nonlinear feature transform, it's still called linear regression. And the main reason for that is basically still that it's linear in the parameters w, and it's also linear in the transformed features, and those are the things that matter for designing algorithms. All right, so a big example of a use of a feature transform is to fit a nonlinear function. So if we have, even if we have, let's say, just one input variable, call it x, we might like to fit that y is equal to a nonlinear function of x instead of a linear function. And in that case, there's an easy way to do it. We just add in some nonlinear functions of x as our inputs. So for example, if we wanted to fit a quadratic function, we could add x and x squared instead of just x. Or if we wanted to fit like a function represented by the first few terms of a Fourier series, we could add sine x, cos x, sine of 2x, cos of 2x, and so forth. So for a polynomial feature, you might think that you would need a constant, but in fact, as long as your features are centered, you don't. Because the constant would basically just compensate for any lack of centering. So you can drop that constant feature. And if there are lots of inputs, like, let's say you have a 5-dimensional input vector x and you want to learn a polynomial in that, well, you can add, each one of your features can depend on all or only some of your original components of x. And that's going to turn out to be important either later this lecture or the next lecture. All right, and so with a feature transform, again, it's the absolute first thing you do. You do it before centering and before variance normalization, before any of that sort of stuff. Because, well, if you did it after centering, the feature transform could uncenter your variables. Another thing to point out is that if you do your feature transform on your training data, you had better do the same feature transform on your test data, right? Otherwise, you're going to get surprising predictions. And maybe that's maybe that goes without saying, but it's actually worth saying anyway because it's the source of a lot of bugs. If you, for example, accidentally forget to center your test data, or if you center it using a different mean prediction than you used for your training data. All right, so another useful feature transform that, that we could talk about is dummy coding. So dummy coding is good for categorical inputs. A typical example would be like a state in the US. So you could encode a state as an integer from 1 to 50, but if you did that, something weird would happen. You would learn some, so let's say Alabama happens to be the alphabetically first state, so it would be Alabama, Alaska, Arizona, and you would learn some effect of being from Alabama, and whatever that effect was, you would have twice that effect for being from Alaska, because Alaska is 2 and Alabama is 1. And obviously that doesn't make any sense. There's no sense in which any one state is expected to have 2 times the effect of any other state. So, so we don't want that. So what we do instead is what's called a dummy code, which is to say we take an integer from 1 to k and we replace it with k binary features, each of which indicates a single one of the possible values, right? So dummy coding would look like this. Let's say the integer, whoops, sorry, apparently I've got the wrong tool activated. Let's, much better. All right, so, so let's say we have the integer 3, right? That would then turn into the vector 0, 0, 1, 0, 0, and so forth, right, up to the end of the number of possible values, right? And so each one of these possible vectors, it'll have a single feature turned on, all of the rest of them turned off, and that feature, the index of that feature, will tell you what the original value of the variable was. All right, so so dummy coding is basically just that. One useful thing is that a lot of times it's worth picking one value of the variable as a default. So let's say the default is that everybody's from Pennsylvania, and then you omit that one of the dummy codes, the one of the dummy variables. And the reason for that is that if you include all of the dummy codes, and then you center, right? So they all sum to 1, and so after you center, they'll all sum to 0. And so you have a bunch of features which always sum to 0, and that means that there's a linear dependence in your set of features. And if you remember, that caused potential problems for linear regression. And so what we'll do is we'll drop the default feature, and that breaks the sum to 1, and everything works well again. We can do that either for just an arbitrary default, or we can include it. It can even help interpretation. So if you have, for example, that you drop the 1 for healthy and you just include disease codes or condition codes that a patient could have, then each one of the coefficients of the disease code says, well, this is the effect of changing from the healthy state to having this disease. All right, and so the last one that I wanted to go over again is talking about fixing problems. So all of the problems that you can have with a univariate regression, you can still have with a multivariate regression. In particular, things like heteroscedasticity, outliers, and nonlinearity. The fixes are more or less the same. So we can fix outliers with robust loss functions or with outlier removal, and we look for feature transforms to try and remove the nonlinearity. And the nice thing about multivariate regression is that you can try all sorts of nonlinear transforms of your input features in order to make the regression easier, and it doesn't change the multivariateness of the regression. All right, so that is that's the review of the stuff that didn't come through well last time. So as always, continue to ask questions, and we will try to answer them. So let us now move to the next topic. Oh yes, so the next topic was, if you recall, we talked about the bootstrap last time, and cross-validation and all of that sort of good stuff. So here are the notes on bootstrap. And so just to remind, the idea behind cross-validation or bootstrap was that we train our model more than once, right? So we train it several times, and we get several possible sets of parameters. And each one of these sets of parameters, it corresponds to a possible value, a possible model that could be right. And either formally or informally, we interpret these all of these parameters that we get, the set or the multi-set of parameter values that we get, we interpret that as a sample from our posterior distribution over models. And so we can use that to answer questions like, how likely is it that, let's say, a particular regression coefficient falls in the range between 2 and 4. All right. So I just wanted to give maybe a little bit more visual an example. So here we go. Actually, so this animation, by the way, you can download it from the oh, it looks like I'm obscuring part of the animation, so let's get rid of me. Okay, so you can download this animation from the syllabus page. All right, so let us start from the beginning. Come on. Why are we not? Come on. All right, we'll do the animation the old school way, I guess. So. There we go. Okay, so so we have the first method is a holdout set. So we've got here all of these together. This is our training set. And for holdout set, what we'll do is we'll select a holdout group at random and remove them. We fit on the rest like that. Then we put the holdout group back in and we measure the error on the holdout group. So let's say our model here is a classifier, a linear classifier like a perceptron that we're trying to fit. And so just to go back over that again, right? So we start with our training set. We designate the blue data points just at random as being our holdout set. We remove them. We fit on the remainder. We put them back in, and we check how many errors there are. And so here our error estimate is going to be 1/3, right? Because 1 out of the 3 holdout points had an error on it. So the next right, so here's the estimated rate. All right, cross-validation. So we take our training set now and we assign a color to every point. So I've split it into 3 different colors, red, green, and blue here. And what we do is we remove the green group and fit on the rest, right? So here I've left blue and red and fit on those. Then we put back in the green group, and you see we have an error on 1 out of 4 of the green ones. Then we remove the red group, so this is all of them, and we just keep the blue and green and fit on those. We put back in the red group, and looks like there's 2 errors on that. So that's 2 out of 4 in the red group. And then if we remove the blue group, right, we fit on that, and we put back in the blue group, and there's 2 errors on that. And so our error estimate from cross-validation, right, we made 5 errors out of the 12 training points. Right, each training point was in the validation set once. And so our error estimate from cross-validation is 5 out of 12, or about 42%. All right, so Bootstrap, here we have our training data again. And what we're going to do is make a Bootstrap resample of our training data, right? So if you remember, Bootstrap resampling meant to repeatedly draw with replacement a training example from our training set until we get the same size training set. And so what's going to happen is that some of our examples disappear and other ones get replicated. And here, just so you can see it, I've jittered the replicated ones a little bit, but really they're exactly on top of each other. They are complete replicates. Oh, somebody is asking how to determine a good size for the holdout set. There's not really a formal rule. The trade-off, right, is that the bigger the holdout set is, the more accurate an estimate of the performance you get, and the smaller it is, the more data you have left for training. And so, my thought would basically be you determine sort of what's the accuracy that you really need to have in estimating your performance, and you hold out the smallest possible holdout set that will let you get that accuracy, right? And you can actually calculate what, for example, if it's a classification accuracy, you can calculate what the standard deviation of your estimate is by looking at the distribution of the sum of a whole bunch of Bernoulli random variables, right? That's a binomial random variable. In practice, if you want high performance, you would probably use Bootstrap or cross-validation instead of a holdout, because what that lets you do is it avoids the trade-off in the holdout, because the trade-off, right, in the holdout is that if you put something in the holdout set, it can't be in your training set, but in fact, with both Bootstrap and cross-validation, you can make your training set as large a fraction of the original size as you want, subject to computational limitations. All right. All right, so here's our bootstrap resample. We fit on the bootstrap resample, and then we take all of the points that didn't appear in our bootstrap resample. So that's typically about 40% of them. The bootstrap sample is called a bag, and so all of these blue points are called out of bag samples. And here it looks like there's 2 of them out of 4 that we made an error on. And we just do that as often as we want. And our final error estimate is going to be our average across all out-of-bag samples of the error, the binary question of whether you made an error on each one of these samples. Right? And so, most so for Bootstrap, and informally, but people do it for cross-validation. We do this f times, and we get f different parameter vectors, and we consider those to be a sample from our posterior distribution over parameter vectors. All right, so that is the visualization of Bootstrap and cross-validation, and that I guess we're done with the notes on Bootstrap and cross-validation and holdout for now, except for possible questions. So somebody's asking about the relationship between cross-validation and overfitting. So cross-validation does not by itself, and same with Bootstrap, they don't by themselves prevent you from overfitting. They just detect it when it happens, right? So in particular, when you fit your model on your training set, which is, let's say k-1 out of k folds in cross-validation, or one of your Bootstrap samples in Bootstrap, you'll get a training error on that sample. And then when you evaluate on out of bag, you'll get an estimate of the generalization performance, the test error. And if those differ a lot, then you're overfitting. And Bootstrap and cross-validation don't prevent you from doing that. They just tell you when it happens. And so what people will do is they will adjust because you can now see when you're overfitting, you can adjust your model fitting procedure to try and reduce it. So you could add a regularizer, you could do early stopping of your, let's say, stochastic gradient descent, or all sorts of other tricks to try, or you could fit a simpler model class, right? So all sorts of other tricks to try to reduce overfitting. These days, probably the most popular is early stopping. So you'll pick a really complicated model class and fit it by stochastic gradient descent, but you won't go all the way until stochastic gradient descent says you're at an optimum. Instead, you'll just keep going as long as a Bootstrap or cross-validation tells you you're not overfitting. So in particular, you don't so just to say again, Bootstrap and cross-validation, they don't stop you from overfitting, they just help you figure out when you are overfitting. Let's see, so somebody's asking about dummy coding and the default variable, right? So just to say again, the problem was that if you include the default variable, you'll get a rank deficiency in your linear regression, right? So what'll happen is that since you, if you include all of the dummy codes, they will always sum to 1, right? You're always from, the options are supposed to be, if you have a U.S. person, they're going to be from one of the U.S. states or I guess territories, and so everybody is going to have one and exactly one of the options turned on. And so since it sums to 1, that will be linearly dependent with the constant feature. Or equivalently, if you center and remove the constant feature, they'll always sum to 0, which means that the dummy codes themselves will be linearly dependent. And so the problem is linear dependence, and we break that linear dependence by dropping one of the dummy variables. Okay, somebody's asking about why bootstrap is necessary, and it sounds really similar to holdout. Bootstrapping is similar to holdout, but it lets you repeat the process. You could in fact repeat holdout in the same way as you repeat a bootstrap. So you could randomly split your data into let's say 2/3 for training and 1/3 for holdout, and just keep doing that over and over. If you did, it would behave quite similarly to cross-validation, in that you could informally interpret it as giving you a sample from your posterior over models, but the only way to get that formal interpretation, right? So people have proved for Bootstrap that under certain assumptions on your model class, you actually do approximately get a sample from your posterior distribution over model parameters. So basically the reason for Bootstrap as compared to cross-validation or to just simply repeating the holdout procedure is this interpretation as a sample from the posterior. And you can actually see at least one thing that's broken in terms of that interpretation for both cross-validation and Bootstrap, which is that your training set is the wrong size, right? So your training set, what you would wind up getting is your posterior for your model after training on a set of 90% the same size as your training set. Whereas Bootstrap, you wind up getting the interpretation as a sample from your posterior after you train on a set of the same size as your training set. All right. In practice, that difference isn't necessarily all that important, and so probably the single most common thing to do is to do cross-validation. It's not very common to do repeated holdouts, but you could, and I see no reason why that wouldn't work really well. And Bootstrap is actually not that common. I'm not sure, probably historical reasons, it's sort of the least well known. But they're all all of them have in practice very similar properties. All right, so all right, so I think we are now back up to all right, I think we've now covered sort of reviewing all of the questions that people had about previous lectures. So I think now is a good time for us to release a quiz. And so what I'm going to do is post the quiz. I'm going to go ahead and post it on both Piazza and Canvas. I'll post it on Canvas first. And we'll pause the lecture stream for a little while to let people work on it. Just give me a second to actually make the post. For whatever reason, Canvas is being slow today. So it's going to get posted under quizzes. All right, it should be live on Canvas. Oh, whoops, I accidentally... all right. Forgot to include a point value. There we go. So it's going to be the same weight, of course, as all other quizzes. All right, so we're going to pause the stream now and give everybody a chance to work on that. And we'll be back in 10-15 minutes after people have had a chance to work on the quiz. All right, hello everybody. So not everybody has finished the quiz, but at least most people have had a chance to start it. So I think I'd like to get back to talking about the notes. If you're still working on the quiz, feel free to pause me. There's not going to be any more assignments during the class, and then come back and watch the rest of the lecture video later. And of course, feel free to continue posting questions about the quiz on Piazza, and we'll do our best to answer them. So the next thing that I wanted to talk about was variable selection. So there's kind of a nice algorithm for variable selection that uses a lot of what we've been talking about. So I wanted to go ahead and describe that. And the algorithm is called forward stage-wise regression, or more specifically, incremental forward stage-wise regression. There's a ton of algorithms for this. Maybe the most popular is lasso for in linear regression. Incremental forward stage-wise is also a way to do variable selection in regression. The algorithm, the incremental forward stage-wise regression algorithm is actually a lot simpler than lasso, and so we're going to cover that one. And it actually works equally well, or sometimes even better, in practice. So, so it's a good one to cover. So, in order to explain it, it uses this thing called steepest descent, which is a variant of gradient descent. So if you remember, in gradient descent, you are trying to minimize a function, L of w, with respect to w, and to do so you repeatedly update by subtracting a multiple of the gradient from your current parameter vector w. Right? So it's more complicated seeming, but we can actually write the exact same update as the solution to a minimization problem. So argmin means to take the value of v that minimizes the following expression. And so this expression is going to be two terms. One term here that says to stay close to our current parameter w, and that's weighted by a factor 1 over eta. And then this other term here, this is a first order Taylor expansion of L around W, right? It's L of W plus the gradient of L at W times the difference. All right? And so what this says is, okay, you know, maybe I can't directly minimize W, but what I'll do, can't directly minimize L, but what I'll do is I'll make a first order Taylor approximation of L around my current parameter vector, and I'm going to minimize that. But while I'm doing so, I'm going to stay close to my current parameter vector, because I know that the first order Taylor approximation is only valid in a small region around my current parameter vector. All right, and if you work it out, which I did down here, but we don't actually have to go through this math. You can do it if you like, but if you just go ahead and carry out this minimization, you'll discover that in fact the update is to set the new parameter vector to the old one minus a multiple of the gradient. And so this is kind of a nice interpretation of gradient descent. It says that we're trading off these two quantities, staying close and making L smaller, and this learning rate parameter controls, the eta controls the trade-off. All right, so steepest descent is just like gradient descent, except that we change the small update term. And the way we do it is we use a different norm. So instead of saying Euclidean norm, we have to stay close, we'll use another norm like the one norm or the max norm, the infinity norm. So the one norm is the sum of the absolute value of components of v minus w, and the max norm is the largest absolute value of any component of v minus w. And so if we look at that, right, so we'll go ahead and get rid of this so we have some space. All right, so if we look at that, right, so here's an axis. Let's put our current parameter vector w at the center. We can always shift our coordinate system so that that's true. And what steepest descent, gradient descent says is that we would, our new update is going to be somewhere within, you know, a small ball around W. right? So that's 2 norm, which is the same for gradient descent, right? So if we instead say that we, instead say that we want to stay within a 1 norm ball, so that 1 norm ball looks like this, right? If you just plot a level set of the sum of absolute values, you'll get a diamond shape in 2D. In 3D, it'll be an octahedron, and in 4D, it'll be, you know, something that we don't have a name for, right? But, so this here is the 1 norm. And then if we plot a level set of the infinity norm, right, it's going to look like a box instead of a, right, and so this here will be the infinity norm. And so what does that mean? If we substitute in the 1 norm, right, we'll have a higher tendency to go to a corner here of this 1 norm, right? Like we're trying to go in the direction, let's say that the gradient is pointing this way, gradient of L at W, right? And so if we, actually let's say it's the negative gradient, that's the direction we're trying to go, right? And so with 2 norm, we'll just go in the exact same direction, right? So here we'll get gradient descent, right? And if we, if you just try, you know, going within this 1 norm ball as far as we can in that direction, we'll go here, right? So this is the 1 norm. And if we do it within the max norm ball, we'll go here. This is the max norm. Right? And so we go to a different place. We consider a small update to be very different depending on what norm we use in this small update term. Right? So if we go here, right, this expression is almost the same. The only difference is that we substituted a different norm, like the 1 norm, for the stay close term. And so this is called steepest descent. And you can see that by changing the notion of what it means to be a small step, we change the direction that we go in optimization. We don't change the optimum. If we keep running forever, we'll get to the same spot. But it can change how fast or slow we get there, and maybe even more importantly, if we use early stopping, if we stop the optimization before we're done with the optimization, before we get to the minimum, we will have taken a different path, and so we might get to a very different point. And in particular, an important thing is that, so you know, we show this example here. Each one of these different norms is associated with a different property. And if you, you'll wind up taking a different path. And in particular, if you look at what the 1 norm did, right, we stayed on the coordinate axis here. So what the 1 norm did was it encouraged us to have a sparse update to our parameter vector, and if we keep making sparse updates, our parameter vector will tend to stay sparse, at least if we start at a sparse point like 0. All right. So in order to run steepest descent efficiently, we need to be able to find these update points, meaning we need to be able to solve minimization problems that look like the one that we did before, right? So if D is our update direction, the difference between V and W, and G is our gradient, the optimization problem looks like this. And in general, the optimization problem could be difficult, but for 1 norm and for infinity norm, it turns out to be easy. And I've just written down the solutions here. You don't have to necessarily pay a lot of attention to what the exact form of the update is, just to know that there's a really efficient way of finding the steepest descent update point for both of those 2 norms. All right, so that is steepest descent. And given steepest descent, we can define the forward stage-wise algorithm. And it's actually really simple. What we do is we're trying to solve a linear regression problem, and we solve it, we could solve it by gradient descent. So what that would mean is we would build the least squares objective out of our training set, the sum over all of our training points of the true y minus the w times xi, squared difference. So that's the least squares objective. We could minimize it by gradient descent, but if instead we minimize it by steepest descent using the one norm, we get incremental forward stage-wise regression. So what does that mean? Because we're using the one norm, we're trying to keep our weight vector sparse as long as possible. Although, because again, we get to the minimum no matter what, we'll get to, if we run optimization forever, we'll get to the least squares solution. But what we do is we do early stopping. We might do early stopping based on a holdout set or based on cross-validation or bootstrap. And in order to get an accurate early stopping point, we use a fairly small learning rate. All right? So once you understand steepest descent, and once you understand the least squares objective, incremental forward stage-wise regression is a really simple algorithm. You just run steepest descent using the one norm, using a small learning rate to try and minimize the least squares objective, and you do early stopping using, let's say, a holdout set. You stop when your holdout error starts to go back up. All right, so if we take a look at how that runs, so actually maybe better, well, I'll show a movie in a second. But what happens is that the progress of the algorithm, it starts on the left and it keeps going towards the right. Each one of these lines corresponds to a regression coefficient in a synthetic problem. There are 9 of these regression coefficients. The least squares values are shown as dots, circles on the far right. And so if we run forever, we get to the exact same point that we would have if we had done least squares. But instead, we do early stopping. So we stop, at some vertical slice here, and we pick, maybe we pick here, and we stop where only a few of the parameters, let's say 3 of them, have moved away from 0. All right, so let's do a movie. Actually, before we do the movie, let's do look at the code. Again, you can download this code. What it does is it sets up a synthetic problem, right? So it there's 100 training points, and we generate our true labels using a, the first feature plus the second feature minus an interaction term. And we do, we add a little bit of random noise. And then we set up our least squares loss function. So we center each row of x, and we build some linear and quadratic features, because let's say we don't know which of the features are relevant. We standardize everything, including the outputs, and we initialize with a 0 weight vector, and we start with our residual error, meaning this is we're trying to minimize the sum of squares of residuals, and so we start off predicting 0 for everything, and so our residuals are just equal to our original y's. And for plotting purposes, what I've done here is compute the least squares weights for comparison. And then we just iterate. We repeatedly compute the gradient, and we solve the problem of taking a step. We choose a learning rate and make the step, and then all of the rest of this is just doing a plot. So let's take a look at what the movie looks like. All right, and so if we run, let's go back to the beginning and play it again. All right, so you see what's happening here. So what I've got over on the left is a residual plot, right? So I predict a value y hat, and here's y hat minus y, so we would like the residuals to be small. And Now that the algorithm is done, all of the residuals are as small as they can get. I'm plotting the gradient over here. This is for each one of the features, what's the magnitude and direction of the gradient. And then here, this is what's called the regularization path. It's showing all of our coefficients start at 0, and then as we run the algorithm, they start moving away from 0, and some of them move away first because they're the ones that it determines is most important to move away from 0. So we'll run that again. You can see for the residual plot, it starts off that the residuals are all large, and as we run, the residuals get smaller. And then if you look as well, right here, we start off with all of our parameters at 0, and as we keep going, you notice the gradient is already quite small, right? Even as we go, even when we're about here in the plot. And so we're gonna use, I don't show it here, but we're going to use a holdout set to decide where to stop, and hopefully we'll pick a point where our weight vector is still sparse. All right, so that is the incremental forward stage-wise algorithm. Again, you can download that video and watch it at your leisure. And I just wanted to, the reason we showed that is that I just wanted to show an example of what a variable selection algorithm would look like. And this particular one gives us an opportunity to use a lot of the concepts that we've learned, and happens to be a really good one in practice. All right, so we're getting kind of close to the end of the lecture period. Let me see if it makes sense to keep going. No, actually, I think that works out pretty well. We'd have to, there's an entire new topic that we'd have to start, and I don't think that it makes sense to talk about it for 8 minutes. So let's go ahead and stop here. And my office hours start now, and I'm gonna keep watching Piazza and trying to answer questions for people about the quiz. So I'll talk with you guys later.